Hello, this is the first of two asynchronous lectures for Monday, June 8th, 2020. This is on the topic of kinetic friction. Basically, what I want to talk about today is a special form of friction. So we have to go back to the definition of friction. So friction is the name of any force that is applied or results from the interaction of two bodies parallel to a surface. So if I have a surface, that's a surface like that, kind of a floor or tabletop or whatever, and I have another body like a block, something like this, that sits on the surface, then there could be a force of, then if there's there could be forces resulting from the interaction of this block with this surface. The block has a surface. There's two surfaces involved here, one for the block, one for the table, for example. And there could be, depending on the motion of the block and the other forces on the block, there could be a force on the block that results from the surface. And if that force is parallel to the direction of that surface, so this is perpendicular and this is parallel, any force either this way or this way on the block is by definition a force of friction. And by the way, just so we remember, if there's a force of friction on the block due to this surface, there has to be a force of friction on this surface due to that block. So in other words, just as there has to be a force of friction going this way, there'll be, by the third law, an equal and oppositely directed force of friction this way. So in general, so by the way, it doesn't matter what kind of force, doesn't matter any other details about this force other than if it's parallel to the surface, that is the definition of friction. And that's all you need to know. As soon as you say, oh, it's called a force that's going this way, or could be a force going this way, then it's a force of friction. That's what we care about. An alternate idea of friction, it's a concept of friction, is that friction is a force that acts so as to attempt is the right word, attempt to resist the motion of one force relative to another. This is actually not that useful a definition. It's in particular a treacherous definition for trying to figure out which way the force of friction is actually applied. A better way of figuring out which way the force of friction applies is either to A, use Newton's second law to figure out what the motion tells you about which way the force must be, or B, just pick a direction, do the calculation, and if you get a negative sign, you've got it 180 degrees backwards. So, but in some sense of the word, friction tries to keep the two surfaces together. When friction succeeds in keeping the two surfaces together, in other words, if I say no slip, which is the same as no slide, neither slipping nor sliding, the two surfaces are stuck like glue between them somehow, then this is sometimes called static friction. Static, not because nothing's moving, but because one surface doesn't move relative to the other. So this idea of relative motion is important. You pick one surface, you say that's my definition of the coordinate system, and if the other one surface is moving relative to that surface, then it's not static. But if they're at the point of contact, no slipping, no sliding, that's static. A block just sitting on a table, that's static. A block like this block here, this eraser, if I come along and I push the eraser and it doesn't move, there's a force, then that's not, I have to push it lightly and it doesn't move. That's static. As long as it's not moving, not slipping, not sliding, that's static. Another common example of static friction is a wheel, a rigid wheel that is rolling on a surface. Now, somewhat confusing since by definition, the wheel itself is moving, but at the point of contact, if there's no slipping and no sliding, and that's typically what happens, a car wheel rolling or a train or a bicycle, typically, ideally, no slipping, no sliding, no skidding, no squealing, whatever you have. All of that falls in the category of static. And the key issue is in this case, the force is equal to an unknown quantity. You don't know what it is. There's no way to calculate it except using Newton's second and third laws. But there's a special case of friction where if there's slipping, or sliding. In other words, if one surface is moving with respect to the other, then I can then this kind of friction is what we call kinetic friction. Somewhat confusing because static and kinetic implies no motion, but really it's not the motion of the body, it's the motion of one surface relative to the other. So we call that kinetic friction. And in this case, we have a rule of thumb that is not based on any fundamental law of physics, but corresponds to a empirical observation, a approximate trend that says that we can estimate the value of kinetic friction. So this is so important. Most of the time, the answer to the question, how do I calculate the friction, is the only way to calculate it is to apply Newton's laws. It's this, you might seem perplexing. How can I find the friction? Well, you have the same problem with the normal force and the tension. All of these things are unknown forces. But on the special case where I know there's slipping and know there's sliding, there's a rule. And this is not a law of physics. This is not a law of mechanics. It's a empirical rule. And the empirical rule says the following. The force of friction in this particular case, where it's kinetic, is equal to some coefficient, which we usually label by the coefficient with the Greek letter mu, and often I will put a subscript k to remind you that it's the coefficient of kinetic friction times n. Okay, so this equation, a couple things to tell you about it. The first is that this is well, a couple things. First, this is not a vector equation. The force N and the force F correspond to forces that apply on the same surface. So in this particular case, the normal force, I'll cover that in green, the normal force that's being applied to the block from the surface is perpendicular, not parallel to the surface. So no arrows here. Putting arrows here would be totally wrong. This is not a vector. It's a magnitude. It's the magnitude of the friction. What kind of friction? Kinetic friction. So it's not a vector equation, not vectors. And the second thing that's important is that we won't actually take this into account. But in fact, this empirical relationship is in the real world only approximately true. It's true for values of mu sub k that are relatively small, which is to say not much bigger than 0.1 or 0.2 at the most. And it's true as long as this block and this surface aren't moving very fast relative to each other. So for low values of mu sub k and low rates of motion, this is approximately true, but it's not exactly true. It's not a law of physics. It's just a way of getting a handle on it. So in this particular case, you can calculate the value of the friction, but again, only if you know it's kinetic friction, okay? So we've got that equation. Let's see if we can do a simple example so that we can kind of get a handle on what it looks like. So we'll start with a classic example. Suppose I have a surface of a table, and I've got a block on the table. The block has a mass m, and the block is moving with some velocity v relative to the table, and nothing else is touches. There's no forces applied to it, but there is friction between this surface and that surface. And the coefficient of friction that's associated with that surface is given as the coefficient mu. We'll just call it mu. So in this case, mu equals the coefficient of kinetic friction. So sometime in the past, somebody took this block and gave it a big shove. We're not talking about the past, we're talking about now. So now there's no shove on the block. It's just sitting there, but it's not just sitting there. It's scooting across the table. It's coasting across we'll say that specifically, this is a block and this is a table, like a real table, like a kitchen table. And the block is skidding across the table. And there's a coefficient of friction associated with the interaction of the block and the table, which is a given. So the mass and the velocity and the coefficients are all given. I asked the question, what are the forces? All the forces on the block, and what is the acceleration of the block? Is the block accelerating, and if so, which way is it accelerating and how much? So, well, we know, so let's go. So we've got the diagrams. First step is we got all these coefficients given. We got a diagram. We kind of need to pick a coordinate system, and you have choices here. You could pick, you could make the logical argument that the block is moving this way, and so we'll call this the positive direction x, which is what I'll do. But you can also make the case that the block is decelerating, and therefore, if you want to line up the acceleration in this direction, that corresponding to the direction of acceleration, you could do that too. That's not what I'm going to do, but you can do that too. Either choice is fine. But we don't know the acceleration. Well, we know the vertical acceleration is 0, but we don't know the horizontal acceleration. So we'll say a sub y, in this case that's y, is equal to 0, and a sub x equals something we don't know. That's what we're trying to figure out. What is the acceleration? So I do a free body diagram. Free body diagram of the block. And the block, so I put a coordinate system down to start, and it's just for fun. And the block has a weight, and the block has a normal force. And we won't even bother with, well, we'll bother with it. Let's mess with it. And there's some sort of friction. And again, you may say, which way does the friction point? Does it point to the right or point to the left? But your intuition tells you that if you're watching the block on a table, it will tend to slow down. So that tells you that slowing down, corresponding to Newton's second law, there must be a force of friction that's in opposition to the force. So normal force, weight force, and then friction to the left. So that's our free body diagram. There's no other forces involved. So we'll do Newton's second law in the y coordinate first. That's easy. We've done this about 10 times. We say F sub y equals ma sub y. We know what m is, and we know that this is 0, so that's 0. So we get n minus w is equal to 0. So n equals w equals mg. Hey, okay, we got that already. And then this is the second law in the x coordinate. So we say F sub x equals ma sub x. Well, a sub x is what we're trying to find. We don't know that. So we still have m sub a sub x on the right. And on the left side, the only force we have is the force of friction, and it's going in opposition to the coordinate x. So label that F, negative F. So negative F equals ma sub x. And I've got F, and I've got a sub x, and I don't know either of them, at least not at this point. But over here, I could say, F is kinetic. So in this special case, since I know the kinetic friction, I can use the rule of kinetic friction, which I erased, so let me put it back here. The kinetic friction is equal to mu sub k, the kinetic coefficient of friction, times the normal force. So in other words, negative this thing, which is the coefficient of friction, which in this case I'm just labeling mu, times n, and we already worked out, it's this mg. Mu mg is equal to m times a, these should all be the capital M's, sorry, is equal to capital M times a. All right, and then, oh look, so this actually is the friction. So we know now that the friction is equal to mu times m times g. So we got the friction. And then I just, okay, cancel out the m's. And I get that a is equal to negative mu times g. That's that which is just a sub x, right? So we now know the acceleration, a sub x. So we got the acceleration and we got the force. Now again, in this particular case, because the block is slipping and sliding, and you know it's slipping and sliding because the table is still and the block is moving, So those two surfaces have to be moving relative to each other. In that case, and only in that case, can you use this equation. You can't use this equation if the friction is static. You can only use it if it's kinetic. Okay, that's all for now.